Okay, let's move on and have a look at some more ways, things that SQL Server does when queries are executed. First of all, we're going to look at parallelism. Now, parallelism because the optimization process decides that a query needs to be split across multiple CPUs or cores. It determines that the cost is greater than the cost of executing the plan in parallel is less than the cost of executing the plan in serial. It uses the max stop that you have set on your machine, maximum degree of parallelism that can occur for a specific query that you have set on your system, and it looks at the cost of the exchange operators. Now, the exchange operators are ways that the SQL Server manages the various parallel execution threads. Now, this can speed up a plan. In general, it does speed up a plan, but there are various cases where it could be detrimental to performance. So let's have a look at what is parallelism for a little bit first. On a four-core system, 5 threads are generated. The first thread that is generated is known as worker 0. Worker 0 then spawns 4 workers, one for each core. It passes off the work to each of these workers. So worker 0 is kind of like the manager. Worker 1 through 4 are the actual executing threads that go and execute that work against the CPU. And then the threads come and bring the results back together and hand it back off to worker 0. Now, the thing is with having multiple CPUs working against a set of data is that there's possibility that some could finish before the others. And this means that worker 0 has to wait for every single CPU to finish its work before it can hand the results back. Now, the cost threshold for parallelism is the level where SQL Server will decide between executing a serial plan and executing a parallel plan. Now, the default is 5, and the default has been 5 ever since 1997 when somebody on the optimizer team was working through benchmarks on their local workstation and decided that 5 was a pretty good number at that time to decide between running a plan in serial or running a plan in parallel. This is definitely one of those configuration options that is a little bit outdated. When I go and configure a SQL Server, one of the first things I do after installing SQL is go and change this number. I change it to 25 or 50, depending on the server, and then you got to monitor the parallel plans that are executing against your server going forward to see if that is a good enough number or not. Now, we haven't talked about max degree of parallelism here yet. Max degree of parallelism by default in SQL is 0, which means that all CPUs could be used in the execution of a single query. That is another number that I change, and I change that from 0 to the number of cores in a single CPU up to a maximum of 8. So if you have 4 core CPUs, you change it to 4. If you have 8 core CPUs, you change it to 8. If you have 10 core CPUs, just leave it at 8. The maximum maxed up I would set is 8, because anything more than that, the overhead of managing these worker threads is too much for the worker 0 to handle, so it actually causes a performance issue. So definitely change your max stop to 4 or 8 and leave it maximum 8. That's it. Let's go see how that works in action a little bit. Let's go and have a look at a demo. Now, what this code does is it goes and has a look in your cache plans. It mines the data from sysdmexec cache plans to go and have a look at the kind of plans that are being saved in your cache. And what we see over here is that we see a large, a number of procedures, of prepared plans, and of ad hoc plans. If you have a server that a large number of people are running ad hoc queries against, you're going to see total plans, ad hoc plans in the plan cache that are going to be pretty high. If you have a server, a data warehouse server, or sometimes an OLTP server, where the ad hoc plans are way, much higher than any of the prepared plans or stored procedures that are stored in your plan cache, then you may want to go and look at changing up the configuration of your server a little bit. And this is another little performance tuning tip. If you look under the properties of the instance of your server, you go under properties here and you go to advanced. There is a setting which is called optimize for ad hoc workloads. If you have a large or a high number of ad hoc queries being executed against your server as opposed to stored procedures or prepared plans, then you may want to go turn this to true. It is false by default because by default, SQL Server much prefers to use stored procedures. It much prefers to use prepared plans in order to execute its queries. But there comes times in certain situations where your ad hoc plans are a lot higher. The number of ad hoc plans being executed on your server is a lot higher than those of prepared plans or stored procedures. So then SQL Server does provide the option for you to optimize for ad hoc workloads. It changes up the way the optimizer works a little bit. It gives more weight to the way that ad hoc query plans are executed and optimized so that your server does work a little bit better with those. But in general, it is a much better idea to work with stored procedures and prepared plans on your SQL server as opposed to having a whole bunch of people running ad hoc queries against your SQL server. Okay, so we're going to move on and we're going to look at joins a little bit. So there are various kinds of joins that people write. There's left joins, inner joins, and right joins, and outer joins. Depending on the kind of data that you want returned from your query is going to determine the exact kind of join that you want to write, that you want to utilize in your query. And obviously, these are the various kinds of syntactical joins that are available for you to go and return the exact specific data that you want to get returned out of these two tables. Now, the way that SQL Server works is that it takes these syntactical joins and it goes and converts them or say translates them into physical joins because it doesn't use these syntactical joins specifically in order to get the data back that it wants. It goes and changes that up into execution plan and goes and changes them to physical joins so that it can return the data back that it needs. Now let's have a little quick look at these physical joins. A nested loop join is used when the table is really small because it goes and compares every single row from the outer table to every single row on the inner table. A nested loop join is used on our smaller data set, and this is where statistics gets really important. If you have two tables of a million rows and you have no statistics on those tables, Query Optimizer cardinality derivation is going to guess one. Remember that we talked about derived cardinality. It's going to guess one. It's going to choose a nested loop join. It's going to have a bad execution plan for these two tables, and it's going to do a million row comparison to another million row table. And that's going to be really small. I mean, really slow. So you really want to have statistics updated correctly so that you can get a good execution plan for your size of your table. Merge join simultaneously reads and compares two sorted inputs, one row at a time. This is very good for medium-sized data sets. And also it's really good when you've got two sorted data sets coming in and getting compared to each other. Generally, if these data sets are not sorted, you will see a sort occurring before a merge join. The hash match join is the big heavy lifter. It's going to take two large tables and it's going to read in rows from the first table. It's going to build a hash table from that data set. Then it's going to probe and hash the second table and then match those rows in the first hash table. And that is a hash match. It's really quick when we're talking about big tables so that it can go through those tables much quicker. There are three types of tree structures when we're talking about hash match joins. There's a left deep when your first table is a lot smaller than your second table. There's a right deep when your first table is smaller than the second table. And then we have a bushy when the tables are pretty equal to each other, because then it can scan things more evenly. There are various reasons to join. When we want to add extra columns into a set of tables and we want to get extra data in from another table, or we want to eliminate rows and we can join rows and look for matches within tables, or duplicating rows, or introducing nulls, that kind of stuff is the kind of reasons that we're going to be going and doing joins in our queries. When we go and investigate queries at the execution plan level, there's various things that we can go and perform during our query analysis. We can look at the estimated execution plan. We can look at the actual execution plan. The estimated execution plan is something that will be generated before we execute the query. The actual execution plan is something that's generated after we've executed the query, and it gives us the actual plan that it used to execute that query. In SQL 2016, what's nice is that they have new ways of actually looking at these execution plans, where you can go and look at live execution plans and look and see what the statistics are. With live statistics, look and see what the execution plan is actually doing, all of that good stuff. Also, right now, we can go and look at statistics. IO for input, output, reads and writes, statistics time for compilation time and execution time. We can go and look at the statistics in an XML version. We can look at the plan in a text kind of version. All of that sort of thing is stuff that we can go and use to go and investigate queries. At the core of SQL Server, we have two parts, two engines running inside SQL Server. We have our relational engine, which is also known as the optimizer engine, and we have the storage engine, also known as the execution engine. And these two parts are what go and investigate our query and execute our query. When a query comes in to SQL Server, it comes in from the user to the SQL network interface. The SQL network interface then passes that off to our command parser. The command parser goes out to the plan cache and goes to see if there's already a cached plan that it's able to use. If our query is not cached, then it passes off the query to the optimizer. The optimizer goes through all those steps that we looked at a little bit earlier. It goes and parses and binds and optimizes the entire query, that sort of thing. Once it has generated a good execution plan, it passes off that execution plan to the query executor. The query executor passes the query plan off to the access methods, and it writes a copy out into the plan cache. The access methods in the storage engine is like the old guy in your company who knows exactly where everything is in the storage closets, and he also even knew where things were in the old building there. The access methods they are responsible for knowing all the physical structures, the objects, the indexes, the files within the database, and knows where everything resides on disk. The access methods goes off to the buffer manager to go and request the data. The buffer manager goes and looks in the data cache to see if the data is in the data cache or not. It's not, so it goes and reads in the data off disk, returns the data to the data cache, and then passes the data off back to the access methods. The access methods, in turn, passes the data back to the query executor. The query executor hands the data off back to the SQL network interface, which sends the data off back to the user. Normally, this all happens within a fraction of a second every time we do a select state. If, however, we have something like memory pressure or slow disk, we could see that our query could take a little bit long. If the data needs to get written into the data cache and the data the memory is under pressure, in other words, there's not enough space for the data to be written into the data cache, then certain parts of the memory needs to get paged out to disk, and this could take a while before our data is actually read into the data cache so it can get passed off back to the buffer manager. If our disk is too slow, then data being returned back to the buffer manager could take a while, and this could also cause our query to be slow. Knowing all the internals of a select statement or the SQL's process gives you an idea of where to look if your query starts becoming a little bit slow. Now, bearing in mind that all of this whole process is contained within the SQL operating system, and the SQL operating system controls all the processes, the memory, the CPU, and the I/O for SQL Server. And we'll have a look at the SQL operating system a little bit later when we go into weights and queues. And we'll have a look and see exactly how the SQL operating system manages all of these things. Now, that was a select statement. Let's go and have a quick look at how this relates when we're going to do an update statement. If we have an update statement, once again, the user passes the query off to the SQL network interface, which goes off to the command parser. The command parser looks at the plan cache to see if there's a plan in the plan cache. There is none, so it goes through and hands the update statement off to the optimizer. The optimizer generates an execution plan and hands that off to the query executor, and the query executor hands that off to the execution plan off to the access methods. Now, access methods, in addition to talking to the buffer manager, goes and writes a copy of the transaction into the transaction manager immediately. The transaction manager is where we get our locks and where the transaction is written out to the transaction log. So we're going out to the transaction log and writing a copy of the transaction there so that we know what happens, what changes are being made to which particular row. The buffer manager then talks to the data cache. At this point, we have dirty data pages in the data cache because it goes and updates these data, and it goes and writes the updated data into the data cache. This data, as you can see, when the buffer manager returns the transaction back to the access methods, that data has not been written to disk yet. That is why it's known as dirty data pages. The access methods return the acknowledgement and the query back to the query executor. The query executor returns the data back to the SQL network interface, which returns it back to the user. At this point, the dirty pages are flushed by checkpoint to get written off to disk. This is known where we have the transaction manager writing the transaction to the log before the data is even read or in from disk or written to disk, is known as write ahead logging. And it's only during inserts, updates, and delete operations that this writing to the log occurs. Things to look at when we're looking at execution plans. If a query reads in some data from a non-clustered index and it needs to go and do a look at the heap in order to find the rest of the columns for the query, that is known as a RID lookup. And if the non-clustered index needs to look back at the clustered index for additional columns, additional data, that is known as a key lookup. There's various things to look for in an execution plan scenario. Mostly we want to look at to see if there are yield signs in the query plans, things like implicit conversions or unmatched indexes or sorts and spills are called out in our execution plans when we execute a query. Try and avoid things like key lookups and RID lookups. Use covering indexes, that kind of stuff when we are executing queries. Linked servers. I'm not a fan of linked servers. They work sometimes, but I prefer to get all my data on one database at a time. The thing with linked servers is sometimes people execute a query not knowing what's going on in the back end. And if it takes more than 5 seconds to return data to a specific web page or an application, the user gets impatient. They kill the browser or they kill the report or whatever it is and they open it up again. And pretty soon you've got 10 or 15 or 20 linked server connections from your database to another database because the user keeps on killing the connection. That is one of the reasons that I'm not a fan of linked servers. It's just that network is typically much slower than disk and CPU and memory can possibly be. So if you run an ETL every night to get the data that you need and keep it on the same database server, that's a better situation than using linked servers. CTEs and table variables are not able to contain statistics, and therefore when it comes time to use large table variables or large CTEs, you are going to have a suboptimal execution plans. Select only the columns that you require. Very, very important. A lot of users just write select star and you're just returning too much data at that point. You're not able to use things like covering indexes at that point. Really try and get your users to select only the columns that you require. That's a very good performance tuning technique. If you see a select star in queries, you should really just pare that down to only the columns that are required to satisfy that query. And that's the end of our querying module. The next module is index tuning, and we're going to go into that next.